sine and cosine and tangent lives, you use them with right triangles, right?
Yeah.
We're going to expand that into using it with different modeling situations, specifically, of course, music. But we can also model yearly weather patterns, right? If you want to.
That Colorado bipolar and it snow whenever it wants to.
Yeah, well, so right now we should be in the coldest part of the year, right?
Yeah, or not.
So if we're in January, we're going to be the lowest average temperature. What happens in July or August? You got your highest average temperature, and then you come back to, let's say we do a 1-year cycle back to January, right? And all these temperatures in here look like this. Your model for yearly temperatures will follow a sine or cosine wave in some way, shape, or form. Okay, so there are applications other than music or sound waves that we could use this for. So you might expand your thinking there a little bit. All right. Okay, so if that's what a sine or cosine wave generally will look like. Okay, we're going to be more specific than that, but I want to point out a few things. Okay, that's one. This is what we call the amplitude. Okay, can you read that?
Yeah.
All right. So that's the amplitude. It's just the height of half of the curve. Obviously 1 to -1 because it's symmetric. Okay. This in music terms is the volume. Okay. Right. So that would be one aspect that we're going to study. Okay. This here is the wavelength. Some people call this 1 cycle. Okay. In music terms, the pitch or frequency is cycles per second. That's where we get our time component in music. Or sound wave. Okay, so lots of words we're throwing around here. It's very heavy science, wordy stuff. So when we add a movement and time component to the wavelength, we get sound waves because they're moving, right? So that example of the G note that I showed you was 392 hertz. Right?
392.
392 of those per second are passing your eardrum. Okay, and your brain interprets that as a certain sound, so you can hear it, right? Whereas an A, I think there's an A at 440 hertz. It's going to sound a little bit higher. Okay. Obviously, your brain interprets that as a different sound. So, hertz is cycles per second. So, there's your music application there. Right? What? Did I not turn it on?
No.
Nice try.
Dude, I'm telling you, I just looked.
It's on. Okay, so everything's on.
Shut up.
Why don't you both stop, please? Because pride is getting in the way of learning right now. Any questions with that? Okay, we'll get into these specifics next week. Okay, for now, all I want to do is teach you these standard sine and cosine graphs. Okay, because there's a lot of different components to them. So this is the equation that you're looking at. Y equals sine x. And x is in radians. So we had to use radians yesterday, right? And this is going to be built completely off of the unit circle. Okay, so when we graph, I used to have a, that'll work. I used to have a trigonometry grid here, but I don't know where it went. Okay. You can go in the negatives, okay, but obviously music is time and we don't do negative time, right? Not going back in time.
You're gonna need time. Things like that, pretty nice, but not I just wanted to make sure.
When we mark on the x-axis or time axis, we use radians of pi over 2, pi, 3 pi over 2, and 2 pi. Okay. That puts us straight on the unit circle. The amplitude and period of the general sine and cosine curves is 1, or the amplitude. I don't need to go that high. It's a little smaller. You can set your 1 and -1 wherever you want, but the graph will not go beyond these y values because this number out front is a 1. Next week I'll show you what happens if you put a 10 out there. It goes from 10 to -10. Right? So, but for now we're just studying the general curve. Okay. Let's see. Yeah. So we have the unit circle, right? What value, okay, we want to plot the point at x equals 0, right? So if I have x of 0, my y value is sine at 0, correct?
Yeah.
What's the sine at 0? You should have it memorized. It's 0. Yep. 1 is the cosine,
Well, that makes sense.
0 is the sine, right? So we're going to put a point at 0, 0. Right? What's the value at pi over 2?
Pi over 2 is 1.
Sine at pi over 2 is 1, right? And then we're going to keep going at these certain points. What's sine at pi? Oh, cosine at pi is -1. Sine is 0. All right, so we've got our first half of the cycle, right? What are we going to have at 3 pi over 2? Yeah, -1. And then at 2 pi, we're going to end up back at 0. So your curve, boom, right there. Okay. That's your generic sine curve. Okay. What's the amplitude? Yeah, the amplitude is 1. Okay. The period, did I mention that on the last slide? Okay. There's another word for wavelength. That's when it repeats. Like I said, lots of words here. Is 2 pi, because that's when it starts to repeat, right? So if we kept going, the graph would just keep doing this. And we can go on for an infinite amount of time. Okay. That's weird. Okay. What's the y-intercept?
0.
0. Yep, right there. And we could, if we wanted to, again, we could just
Is there, so like,
keep going.
is there like,
Okay.
so like, is there like a linear equation for that?
This is not
No,
linear.
I know, but like, is there an equation that will give you an outcome like that? It's just anything that we do in the
Well, that's what this is.
Oh, wait, cosine.
So we did not bound, well, let's say we are graphing it from 0 to 2 pi. This is what we graphed, right? And when you graph these on Wolfram Alpha, I'll show you how to restrict this so that it only graphs 2 or 3 or 4 of these. Okay? So this is what we graphed for now. If you took this away, we would not have any restriction. All right, what are the x-intercepts? How many x-intercepts are there? Okay, on this interval, there are 3, right?
Oh, yeah,
But there are infinite number on the open interval, right? Okay, so what are these?
X-intercepts is 0.
0, pi, and 2 pi, right? Can you think of a way to write that without writing the numbers?
0 to 2 pi? No.
I would say pi times k, where k is some integer. Do you remember that from earlier this year?
Yeah, I thought.
Okay, so an integer would be -1, 0, 1, 2, 3. So I could plug any integer in here and I would get an x-intercept on the open interval, right?
Yeah. So if you were to plug in.
On this one, I plug in 0. K is 0.
Okay.
I get 0 as an x-intercept.
Oh,
Right.
okay. So if you plug in, so if you plug in pi.
So plug 1 in for k, you get pi output. Because k is an integer,
Oh, okay, that makes sense.
whole numbers with
That makes
negatives.
sense.
Okay. So if I wanted some x-intercept out there a long ways, I could plug 1,000,000 in here. 1,000,000 pi is an x-intercept of sine x.
Wow.
Okay. What else is there we could? Oh, there's lots of info here. Maximum value.
1.
Yep. 1 at what x value?
All of them. No, at all.
In this specific case, it's at pi over 2,
Yeah.
right?
How do you write that?
Again, how would I write it? Let's put these in red. For no restrictions. It starts at pi over 2, right? And how often does it repeat? Every 2 pi, because that's a period, right? So pi over 2 plus 2 pi k, if you want to generalize it. So every 2 pi, it's going to have a maximum. The nice thing about these is they're very consistent. Okay.
Is that plus?
Plus, yeah. So pi over 2 is the first maximum, and if you want to find the next one, it's plus 2 pi, plus 2 pi, etc. Okay. We can do the same thing for a minimum, right?
-1?
Yeah. Do you want me to write that down? Okay. So we have max, min, x-intercept, we have y-intercepts. Let's see, we could talk about in behavior, but there's really nothing that happens there. Minimum, maximum, x-intercept. Oh, domain and range. How could I forget that?
That's easy.
What's the domain?
The range is -1 to 1.
On this one here, it's 0 to 2 pi, right? That's all I've graphed with my restriction.
Oh yeah, domain's
Okay. If I were to do no restrictions, what would the domain be?
0 to -3.
There you go. Yeah. All real numbers. You could write it like this. You could write it like this. You could write it like this. welcome to math, where we say things 10 different ways.
Like Spanish.
And English. Okay, what's the range of that function? Negative 1 to 1, yeah. Remember, y values, that's all it is. Right, so you've got yourself a sine graph, and all of the information that pertains to it, we just didn't write down the minimum, or minima. Okay. So, lots going on there. And that's why we take, like Tuesday we'll take a chunk and do amplitude and period. Wednesday we'll start to work with vertical translations, horizontal translations. There's just a lot of stuff to consider. Okay. Questions? Lovely. How about cosine?
That was just sine.
Yeah. Here's what's really nice about cosine.
The opposite.
It's very similar. We take, let me see if you can figure out how they're the same and how they're different. We'll compare and contrast them. We'll do a little, it's easy? Okay, we'll see.
Why don't you just plug in the cosine into the sine?
Okay, again, same setup. They have the same period, 2 pi units. They cycle in the same manner. We'll just go, again, same amplitude. Okay. I'm not putting the unit circle up there this time. What's cosine at 0? 1. Cosine at pi over 2?
0. No. Wait.
Are you sure?
Which one is that?
It's 90 degrees.
Oh.
0. Okay, what's cosine at pi?
1.
Negative 1. Can you guess the next one?
0.
0.
1.
If there's your cosine graph.
Oh,
Okay. If I continue this,
It's the same thing, just shifted.
how much is it shifted?
It's shifted over like, I'd say, like a half of it.
Look at sine.
Yeah. It's shifted over half shifted.
How many units is that? What unit is that?
Pi.
Pi over 2?
It's shifted
It's
over
just,
pi
you
over
just
2.
take it left, correct? So you're translating left pi over 2 units. They're the same thing. It's just, we literally took sine and went, whoop. Okay. So it's going to change the locations of the y-intercept, the x-intercepts, the maximum, the minimum, all that stuff. But the domain, the range, the amplitude, all stays the same. Okay. Yeah. So this is why when you write your music project reports, you will only be working with sine. Okay, because obviously when we do music at time 0, nothing's happening, right? But then we start. Whereas with cosine, we already have something at 0. Okay. It is useful, but we just, sine fits better with music. Okay. Do I need to write down all that info? Range, domain, maximum, minimum?
No.
Okay, so same style of stuff. Okay, but that's your general cosine curve. Okay. Make sure I covered everything. You will obviously get more comfortable with radians as we progress. Okay. So let me ask you a question. Say graph y equals sine x on this interval here.
2 pi to 7 pi?
5 pi to 7 pi. Don't hold it in. you blow a gasket. I read an article about a guy that held a sneeze in, ruptured his esophagus. So he had air leaking into his neck. He was in the hospital for 7 days. So don't blow a gasket. Let it go, man.
Yeah,
Okay.
I'll hold my sheet.
Sidebar. Sorry. That was just
Yeah,
recently.
maybe I'll just keep holding them.
How about you just like
Maybe then I'll die.
contain 150 mile an hour spew of germs instead of trying to rupture your own throat?
Maybe then we'll
Okay.
die.
So what are the radian intervals?
Okay, so 5 pi to 7 pi. Obviously, I don't want to put a graph way out here.
Oh, I know.
So I'm gonna put a graph break. Are we okay with that?
Yeah.
So this is a break.
Is that what it looks like?
And then I'm gonna put 5 pi,
6 pi over 2.
and then I'll just go out to here. Okay.
6 pi is-
6 pi is gonna be here, 7 pi out here. What's gonna be in the middle?
Something.
Between a
Something
5 and
with
6 or
five.
6 and 7.
Either one. Both, actually. This is 10 pi over 2, right?
That is?
This is 10 pi over 2.
Oh, yeah.
What's this?
3 pi over
12 pi over 2, so what's
11 pi
between
over
them?
2.
Yeah, 11 pi over 2.
And that
Okay.
one's 13 pi over 2.
Got it. Okay.
That's easy now.
Okay. Okay, I guess you'll get to prove that.
You just made math simple.
If you make a common denominator in denominator-based situation, it always makes things easy. Okay, that's a little tip. All right, what does that graph look like? So what we're looking for is, what is the sine at 5 pi?
Which one's 5 pi?
Exactly, okay.
Mike, pi, are you in a circle on there?
Oh, that's not what I wanted to do.
Ah, sucker.
Sucker. Who to dummy now? Okay, thanks, Major Payne. There you go.
Oh, I just watched that though.
All right, we're almost done, so let's hold ourselves together so that we don't have to go run laps like Major Payne would make us. All right, do you know how to locate 5 pi on this unit circle?
Yeah, you look for it.
Well, it's not printed on there.
Well, if
How many is this? 2 pi, 3 pi's, 4 pi's, 5 pi is the same as pi. It's an odd, right?
Oh, that makes sense.
So the sine value at pi is
-1.
0. So the sine at 5 pi is 0 as well.
And then 11 pi over 2.
And then we're just going to go every pi over 2 units. So 11 pi over 2 is going to be here. Sine is -1. And then we go to 6 pi, 0. You see how we manage that? What's this one going to be? 1, and then you've established your pattern, right? You've just graphed sine on a specific interval. Okay? And the reason I show you that is because some of your snippets of music sound waves will be specific intervals where you have to show the intersection of those waves. You remember in the video they showed several waves intersecting at one spot to show harmony or consonance.
So wait.
Okay, so you'll be selecting specific intervals with your notes to graph them to show where they intersect.
With the unit circle, the one at the top and the bottom, what are those half intervals?
These are, yeah, every pi over 2 units.
So can you go through it again? So,
So you got 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2,
No. 5 pi.
5 pi, 11 pi over 2. You just keep going up pi over 2 units. That's what I've found to be the easiest. Okay. I think we're good, unless you have any questions.
Not perfect. I think we're good.
Perfect is a pretty bold statement there, my friend.
Okay, you know, I'm not sure. Come.
Okay. Okay, what's due Tuesday?
Everything.
6.1. What's due Wednesday?
6.3.
What we just did today.
Yay.
Okay, so radians, homework from yesterday, due Tuesday. I try to space that because it's homecoming week and I was gone in this.
Winterfest.
Same thing. Winter homecoming.
No, but Tom, I don't know what you're talking about. Duh.
6.3. 2 through 12. $58, $60, $63, $64, $67, $68. I can keep going if you want.
Shut up.
Okay, so that's today's work. And then remember you're progressing in your reports as such. And I think you have 5 minutes class left. So take advantage of that time.